Now, continuing from our previous video where we talked about Heisenberg auxiliary principle, or we touched a little bit on the eigenvalues and eigenfunctions. Now, most importantly, let's just go back to what eigenfunctions is all about. I'll just represent it in here as EF. So, eigenfunctions, we did say that is a function that is applied to a specific operator. Let's take for an example omega as our operator over here. So if we apply this eigenfunction to this particular operator, what we get is an observable, and once this observable is generated, our observable is actually a property of our operator over here. This particular observable is also called an eigenvalue. Now, once you're able to understand the eigenfunction and eigenvalue, Heisenberg auxiliary principle actually applies to any pair of observable, which is what we have over here. Now, pairs of observables are actually equal to complementary observables. And now, once you know that this is actually taking place in a subatomic system, complementary observables is a property of an operator, which is what we talked about over here. So operators, they exhibit various properties, and those properties is actually explained in terms of various observables. Let's say for an example, we have the idea of our momentum, which is represented as P. Now, momentum has various interesting properties in terms of the velocity, in terms of the mass, and stuff like that. Those are actually the observables we get from that particular operator, and those operators are actually manipulated by using eigenfunctions. Like, for example, eigenfunctions like d over dx in terms of our x coordinates, or you can apply it in the y coordinates, or you can apply it in the xz coordinates. Now, once we don't know that complementary observables is a property of an operator, therefore, what we say in here is that this observable omega 1 and omega 2, they all correspond to the operator omega 1 here and omega 2 here over there. Now, this is actually respective over here, and these two observables, which is what we're talking about over here, they are complementary only if, take note, only if one, our operator, which are actually arranged in this manner, where our eigenfunction is introduced in there, is not equal to the other way around when you flip your operator 2 for operator 1 over here. So they are not interchangeable, because if they are interchangeable, then for some reason they will be equal. However, if they are not interchangeable, then they won't give you the same result over there. So this your eigenfunction in here is actually applied to your operator number 2, omega 2, while your eigenfunction, the same eigenfunction over here, is applied to your operator 1, where you get a result in here that is completely different from the result over here. Let's say, for example, where you have your omega 1 to be your momentum operator, and on the other side you have your operator 2, which is actually equal to your position vector over there. Now, what you realize is that if you apply momentum function over here, and momentum operator over here and position vector over here, what you get is a completely result, because they are actually different. However, they do have observables which are actually respectively similar with respect to 1 and 1 and 2 and 2 over there. So complementary observables do not commute. That is one thing you need to note. For the order in which they are actually applied, they all makes a difference in this particular case over there. Now, in terms of looking at commutators, now commutators of two operators is actually defined as this particular expression over there. So if you have your operator 1 with respect to operator number 2, what we notice is that there is a difference in terms of actual order between operator 1 and operator 2 when you find the difference between the different order in which they are actually arranged. So what we notice is here is that there are actually two conditions over there. There are two conditions in here. Now the first condition is that if the two operators they commute, the order is actually irrelevant. And once the order are irrelevant, in this case, you get 0 commutators. On the other side, if you have a situation where your two operators they do not commute, then the order is relevant. And once the order is relevant, then we have a non-zero commutator. So that's about it for this particular subject in terms of operators and how some operators are actually commutators and why other operators are non-commutators with respect to the order in which they are actually arranged, and when you undergo a difference between the order in which they are actually arranged. This is focusing on two operators where you have those two operators having their own observables, which is what you have over here, and those observables can be actually expressed in one way or the other when your Eigen function is actually applied in there. So that's about it for this particular subject. Please hit a comment down below, let me hear your thoughts, and see you all on my next video. Be smart. Bye.